continuity and one-sided limits. The one-sided limits were the ones where like we would approach from the left and from the right. Those are the ones with the plus and the minus. That's what the one-sided was. All right, let me just give you the intuitive definition of continuity first, and then we'll do like a formal. So intuitive definition. So intuitive definition. So a function is continuous if it has no holes or breaks. Basically, you can draw it without picking up your pencil. Okay, so a function is continuous if it has no holes or breaks. So is continuous. So continuous if it has no holes or breaks. If it has no holes or breaks. Some people would say that calculus is the study of continuous functions, right? Like it's like a major concept in the class, right? Like continuous functions. You study functions that are nice and have no holes or breaks. So let's look at some examples just to see. So like here's a simple graph. So this would be continuous, right? Because there's no holes or breaks, right? So nice and pretty. So I'll just put cont to be lazy, right? There's no holes or breaks. Okay, so it's continuous. What about something like this? Would that be continuous? What do you think? No, it's got a hole, right? So not continuous. So that's what we mean by continuous. So you can draw it without picking up your pencil. We're going to look at many more examples in a minute. So continuous functions, you can draw them without picking up your pen or your pencil, and they have no holes or breaks. All right, now let's look at the actual definition. So the formal definition, so definition. So the way we define continuity in calculus is we define continuity at a single number, okay? So we say a function f, so a function f is continuous at c, so at a single number. So is continuous at c, okay, if, and there's three conditions, right? You can actually break it down into one, and I'll talk about how. So a function f is continuous at c if, so the first condition is that the function actually has to be defined there. So you can't have a hole, right? So one, f of c is defined. So like you have to be able to plug in the number. So for example, 1 over x would not be continuous at 0 because you can't have 1 over 0, right? So you have to be able to plug in stuff for it to be continuous. You wouldn't be able to plug in a negative number into a square root function, right? So it's not continuous at negative numbers. So it's defined. Two. The limit, when you take the limit as x approaches c, the limit has to actually exist. So the limit exists. I'm not sure if we talked about this. For a limit to exist, it has to be equal to a number. So you have to get like a number, like 5 or 2. Also, for a limit to exist, it has to exist from the left, and also, do you remember, from the right? That was the first day, right? We're supposed to do that today, but we've already done it, so it's going to make things a lot easier. So it has to exist from both directions, okay? So it has to be defined, and it has to exist. And 3, it's a little bit weird. So when you take the limit as x approaches c of f of x, it should be equal to f of c. So not only does the limit have to exist, it has to be equal to the function value at c. So now I want to do some examples that, first let me say this. So note, 3 implies, this is really deep, 1 and 2, and I'll explain how. This is really deep. A lot of other more advanced books, like advanced calculus books, they don't do this. They just say a function is continuous if this happens. Done, right? I like breaking it down better. You'll see why in a minute because it's beautiful. So how? Well, this implies this. So first of all, when someone writes down f of c, that means it exists. Like if someone writes f of 2 down, well, duh, it's a number, right? So it must be defined. so it's defined. Then we're saying the limit is equal to a number. Oh, okay, so the limit exists. So if this is true, both of these are true. Again, when someone writes down f of c, that means you're going to get a number, right? Like if I write f of 2, that means it's equal to something. So it's defined. Done. Okay, the limit is equal to a number. Oh, that means it exists. So this condition implies the first two. So it's a kind of a weird thing that we write down 3 conditions, but all you really need is a third one. It's kind of interesting. I'm going to give you some examples now that are not in your book. Years ago, I used to teach a class called Concepts of Calculus. It's like calculus for like business majors. And in their book, they had this example. It's really good. And it really helps you understand this definition. So let's do an example. So it's a simple question, but it's really good. The question is it continuous at x equals c? Okay, that's the first question. And then the follow-up question is really nice. It's, if no, which condition fails first? So if no, which condition fails first? Fails first. That's really nice. Now I just have to remember the example. I think I can do it. Okay, A. So let's see. Here's a picture. So there's the y-axis. There's the x-axis. Get some soda. It's slow, right? Yeah. Necessary evil. Okay. So here's C. So it looks like this, and there's a little hole. Boom. So the question is it continuous at C? So what do you think? Is it continuous at C? No. So no. So that's one answer, right? That's one answer. Done. Okay. Which condition fails first? 1. Very good. The first one. Everyone see why? Because there's a hole. Yeah, so 1. That's it. That's it. So that's an example of where a function is not continuous and the first condition fails first. People really overanalyze this, right? People have spent, it's a class in college, right? Calculus. People spend a lot of time thinking about continuous functions. And you do this in all kinds of math classes.
We go in order to give us the condition?
Yes. Good, Reese. Right? Is it really Reese? Yes, Reese. You want to go in order. So which condition fails first? Good. B. Oh, okay. I have to think of the example. So here's C. Oh, I think I got it. There's a dot here. There's 1 here. Hey! Hey! Alphonse.
Yes.
Yes. So what do you think? Is it continuous? No. So that's one answer. Which condition fails first? 2. Very good. 2. Because the limit doesn't exist. Because why? Because it doesn't exist from what? From both sides. Yeah. So notice it is defined, right? If you plug in C, you get 1. There's a dot there, right? So that works. But if you take the limit from the left, you get 1. Take the limit from the right, you get something else. They're not the same, so D and E, right? So no, condition 2 fails first. It's a nice problem. It's a nice problem. We're going to do a lot of homework today, by the way. All right. I want to leave it up because we're still using it. So let's do C. I got to think now. Oh, okay. I got it. So here's C. There's a little hole here. A little hole here. And there's a 1 here. And then up here at 2, there's a dot. There's a dot. There's a dot in this case. So is it continuous? No, it's not continuous. Not continuous, right? You can't have a hole, right? And which condition fails first? The third, right? Because the function is defined. If you plug in C, you get 2, right? If you take the limit, you get 1. So the limit exists. But the limit is not equal to 2, it's equal to 1, right? So condition 3 fails first. Condition 3 fails first. They're really like thinking questions, right? Really conceptual, right? Really conceptual. Maybe that's why they had it in that book, in that Concepts of Calculus book, because it's supposed to be like the concepts of calculus. They don't learn a lot of the stuff we learn. Like this class is way harder than that class. This is like way, way harder. They only have college algebra, right? You all have had pre-calc trig, so it's got a whole other year. D. One more. C. Whew. This is the easy, well, so what do you think? Is it continuous? Yes, so finally a yes. So those are all 4 examples. So now you see, right, really what it means, why they break it down maybe, right, why it's broken down. It's kind of an interesting problem. So this is continuity at a number. So a function is continuous like in an interval if it's continuous at every point, right, like continuous everywhere. So like this is continuous everywhere except C, right? It's continuous over here, it's continuous over here, but it's not continuous at C. Okay. Hey, Ethan. Good stuff. So another definition, a brief one, and then we'll do some more problems. So a discontinuity. So discontinuity. So a discontinuity is a point or a number is a point. I'll say is a point, but it's really a number. Okay, is a point where the function is not continuous. Where the I'll spell it, function is not continuous, not continuous. And continuous, I know it's really uncomfortable to spell it. I have to think about it every time. It's C-O-N-T. Oh, do you remember how to spell it? I-N. What goes next? U-O-U. What the heck is that about, right? It's so weird. I don't like it, but I'm with it. It's not as hard as other words like separable. How do you spell that? Like, oh, it's got 2 A's and an E. So continuous. Math makes you good at spelling certain words. So continuous. So in this case, like it's not this is a discontinuity. So why did I write this down? Well, there's 2 types of discontinuities, and this will be on your test. So it's removable and non-removable. I have to write this down. So removable discontinuities. So 2 types. I'm going to say 2 types, so I don't have to write it twice. 2 types. There's more, but these are the 2 types we care about of discontinuities. What a big word. Discontinuities. 6 syllables. Discontinuities. It's ridiculous, right? It makes you sound smart, I guess. Like you go out like to dinner with your friends. Yeah, I'm looking at discontinuities. Like, so 2 types of discontinuities. So removable. Basically, removable means that you can remove them and make it continuous. So they can be removed and everything is good. So can be removed. So that function, that doesn't really help us, but I'll write it because you're supposed to learn stuff. And this is the actual real definition. So it's not going to help us at all. But I'll give you something that will help you in a minute. So basically, it can be removed. You can make it better, right? There's hope. If you have a discontinuity and it's a removable one, you can remove it and fix the function, okay? Then you have non-removable discontinuities. I think that's one word. It's hard to say it, right? Removable, non-removable. What do you think a non-removable discontinuity is? What do you think that means? It can't be removed. Yeah, so I'm just gonna say not removable. That's ridiculous. It's kind of like, duh, right? But it's worth it. It's worth it. Yeah, that's what it says in my notes. Good. Good, I'm skipping all that. Okay, I guess I should do some examples. So, fact. I don't even think this is in my notes. I don't even know if this is in the book, but this is useful. We are barely going to use this, but this is an easy way to determine if a discontinuity is removable or non-removable. This will help us in the harder homework questions. So let x equals c be a discontinuity. This is really key. This will let us do some of the hardest homework questions, the ones with the piecewise functions and stuff. We're going to do them today. If you take the limit as x approaches c of f of x, and it's equal to L. So in other words, if this limit exists, so in other words, if this exists, I could just write exists. I'll leave it like that. This is equivalent to saying This means equivalent to. So whatever is written here is the same as whatever is here, okay? So this is a double arrow, okay, like this, like this, like this, and then you have to draw the arrows, so like this. This is a symbol for mathematical logic. Okay, then x equals c is removable. Yeah, that's right. Oh, I totally winged that. That's correct. Yeah. That's 100% correct. So if you take the limit and it exists, it's removable. So if the limit exists, it's removable. If it doesn't exist, it's not removable. So this means the limit exists. Because whenever you say it's equal to a number, it means it exists. So if you take the limit and it exists, it's removable. If it doesn't exist, not removable. That's a lot of work. Taking limits is hard. So we're going to be doing easier problems first, and then we'll do the harder ones later. Like there's some harder limits with the piecewise functions and stuff. But this, I'm going to put this in a box because this will help you. And again, I don't know if it's in the book. All right. Let's do a problem, like a test level question, so that you get an idea of how this works. So we'll have I'll call it an example. And this is one that I think was every semester, it's on every test, no matter what, right? You always have one like this. So we have, let's say, x plus 1 over, let's make it test level. So I won't make it easy, like not super easy. 3x plus 2. Can you see it okay?
Yeah, 3x plus 2.
Yeah, I'll write bigger. I'll write really big. I'll write giant. Here. And the question wants to know, what are the removable and non-removable discontinuities? So fill in the blank. Removable and non-removable discontinuities. What are they? Right? The removable and non-removable. So solution. So something happens to the bottom of this fraction. What can you do on the bottom? Yeah, what's that called? Factor! Yeah, factors, I hope. If I did it right? Does it? Okay, good. Starting to sweat. All right, f of x. This is why I messed up in my other class and I lost points when I was on this board. It's like trauma. X plus 1, right? And then on the bottom, I think there's an x here and there's an x here because they have to multiply to x squared. Two numbers that multiply to 2 and add to 3. 2 and 1, 2 and 1, 1 and 2. And they're both plus or minus? Plus, yeah, plus. Beautiful. What cancels now? X plus 1. By the way, obviously negative 2 and negative 1 are discontinuities, right? It's not, so these are disconts. I usually don't write this on the board, but why not? Let's be different. It's a new decade. So these are the discontinuities, right? Negative 2 and negative 1. Yeah, it is a new decade, right? I read that on the internet somewhere. Like, oh, it's like, oh, new decade. Like, whoa. Like, it's right. It's the beginning, 2020. It's kind of crazy, right? Nuts. This cancels. So you get 1 over x plus 2. You probably don't remember this, but I'll ask anyways. When you have the canceling like this in a rational function, which is this, what is that in the graph? It's a what? It's a hole. It's a hole! Yeah, it's a hole. It's a little hole. So whenever this cancels in something like this, it's got to be a rational function, okay? If you have absolute values, game over. It's got to be like this, like x's and x's. If you have something like this, you have a hole at x equals negative 1, right? Holes are always removable. So holes are always removable. So holes in a rational function, let me take that back. Holes in a rational function are removable. But what's a rational function? A polynomial over a polynomial, right? So you have powers of x and everything's a whole number over powers of x and everything's a whole number. That's what a polynomial is, okay? It's like x cubed is a polynomial. Square root of x, not a polynomial, right? So holes in rational functions are always removable. And then here, we can find something here. This, if you set this equal to 0, you get negative 2, right? What is that in the graph? Do you all remember? A vertical asymptote? Yeah! This is a VA, right? It's a vertical asymptote. So VA, so x equals negative 2 is a VA, right? Vertical asymptotes are always non-removable. So I'll come over here and write that down in a minute. So holes in rational functions are always removable. Vertical asymptotes are always non-removable. So very, very useful. Nice test question, right? Because it's pretty easy to factor. One semester I put this on the test and I made it up wrong and it was impossible to factor. It didn't trick anyone. People were like, haha, no discontinuities, or like, yeah, that won't happen. Okay, I'll make sure it's correct. So step one, you factor, cancels, cancellation leads to a hole, right? And then from there. So holes in rational functions are removable and vertical asymptotes are non-removable. You want to try one? Let me give you another one. Here's another one. Should I write that down about holes, or did you already write it down? You already wrote it down? Okay. Then just do this one. Here we go. Try this one. Okay, I got an idea. Here we go. Not so easy. No. I was thinking like, no, it's going to be, I just thought of a harder one. Here we go. Game over. Boom. I think this was on an old test. This exact one. It's ridiculous. So same thing, removable and non-removable. And take your time. So you show all the work. I'll give you a couple minutes to try it. I'm going to yeah. So the bottom should factor, right? So solution. So we have g of x equals x. What can we pull out in the bottom? An x, yeah. It makes it a little bit different. It makes it a little bit weird. This would have been a bad first example, at least in my opinion, because it's a little bit trickier to find the hole. This cancels. So where is the hole in this case? X equals 0, right? Because the question is, I probably should have said this and I didn't say it. The hole happens at whatever makes this 0. So here, -1 makes this 0, right? So if it was like x minus 7, then it would be 7. If it's x plus 4, it's -4. If it's x minus 1999, then it's 1999. So here the hole is at 0. Is this removable or is it non-removable? Removable, yeah. So you can just put 0 here. You don't have to put x. The homework is really picky. In 1.5, you'll be finding vertical asymptotes. In that case, you do have to put x. In this case, it doesn't matter. I'm going to put it because it looks weird without it. So, and then this is a VA, right? X equals 1. Would this be removable or non-removable? Non-removable. Good. Easy, solid test question, right? So the test is actually, all the tests are actually really straightforward if you know how to do all the questions. So, yeah, like you could do it in 15 minutes, like maybe 20, 15. Like, yeah, like a lot of it's conceptual. It's like, oh yeah, like, All right, let's do something else. Maybe, yeah, okay. Yeah, let me look at the homework and we'll do some homework problems, I think. So that might be the best route to go. Let me sign in. See if this works. Password. Okay. The good news is next time is also an easy day, by the way. Like next week on Wednesday, it'll be easier than today. It's kind of nice. Gives you some like catch-up time. This homework is pretty tough. Like this homework 1.4, it's pretty tough. Let's see how hard it is. We'll come back to that. I'll do that in a minute. Okay. All right. Let's do this. Let's do this. Trying to think of a good problem to do. Yeah, I think we should do this. We haven't done this yet. So we talked about one-sided limits. It was part of the topic for the section, right? Let's take a one-sided limit really quickly, just for practice, okay? So let's compute the limit. This is tough. As x approaches, and let's approach a positive number. Let's just go to 2, okay? And let's approach from the left. And the expression that we have to find the limit of is the absolute value of x minus 2 over x minus 2. Okay. I think there's only one of these in the homework, unfortunately. Okay. So this will be a nice question. This is really tough. I don't think we've done anything this hard so far in the course. So If you plug in 2, you get 0 over 0, so it doesn't work, right? So how do you get rid of this? How do you get rid of the absolute value? You have to use the definition, right? So I don't know if you remember, the absolute value of x, it's a piecewise function. If you don't remember, it's okay, now you know. So it's equal to x if x is greater than or equal to 0, and it's equal to minus x if x is less than 0. It should be an if here, but I didn't write it. It's not necessary. So it's one of those two, right? That's the actual definition of absolute value. Sure, it's the distance between x and 0, but you can think of it this way as well, okay? So we have to strategically get rid of the absolute value in this problem. So this is the absolute value of x, right? So you notice, if x is positive, the absolute value of x is equal to x, right? If x is negative, the absolute value of x would be equal to, what would it be if you use this definition? Negative x, right? So like just for fun, let's say you know x minus 7 is negative. Let's say you know that. Then you take the absolute value of x minus 7. What would that be here? What goes here? Negative parentheses x minus 7. So if this is negative, when you drop the absolute value, you have to put a negative sign in front of it, okay? If it's positive, you can just drop the absolute value. See how that works? So like one more, I'll erase it. Say we have x plus 4 greater than 0. And you have the absolute value of x plus 4. Do you need a negative here? No, you don't. Good. What if you have x minus 20. And it's less than 0. Jeez, okay. And then you take the absolute value of x minus 20. I can't even write it. It's so weird. Do you need a negative here? Yes. Do you need parentheses? Yes. Very important. Good. Okay, so now I think we can do this problem. Okay. So this is going to help you. There's a couple of ways to explain it. I think that might be better than what I was going to do. So that's really efficient, right? That's how I do it. Okay. So now let's do this problem. So solution. So we're approaching 2 from the left. So I like to draw a picture because I love pictures. So this is 2. And we're coming from the left. So here's x, and it's traveling this way, right? It's going to 2 from the left. So that means that x, is x bigger than 2 or is it less than 2 based off this picture? Less than 2, so I'm going to write that down. So you draw the picture, you plot the number, you draw, whenever you have an absolute value, like this, and a limit, a one-sided limit, the way I always do it is I draw a little picture, figure out which way it's going, create the inequality, and now watch this, you can subtract 2. So you get x minus 2 less than 0. It's beautiful. This is math. This is amazing. I love this problem. It's so beautiful. And now look, now we can do the problem because this is the limit as x approaches 2 from the left. And then now we can replace the absolute value, right? Do we need a plus or a minus up here? Oh, you get it! Yes! Oh my God, yes! This is most people do not get. This is like really tough. And then we have this down here. So if it was greater than 0, it's just a plus. Hardcore. This is hard. This is tough. This is tough. I sat in once on another teacher's class, calculus teacher. She's really good teacher. She doesn't teach here anymore. And she was doing stuff like this. And she didn't do this. And I felt like, yeah, she doesn't do it, but I do it. Like, I felt good. But she did like 20 examples. So we do like 2, so trade-off, right? She would make him do it like with intuition. And you can draw a picture too. You can draw the graph. And you can do it that way as well. But it's a good skill to have. They cancel. So this is going to be, whoa. I don't know what I'm doing. It's not -1. It's just a negative sign. What does this become when they cancel? What number do you get here? -1. Yeah. I'm going to put it in parentheses just because it looks better. That's really ugly. It's too late. It's better. And then you're taking the limit as x approaches 2 from the left. So you just get -1, right? Because you plug it in, there's nothing to plug in there, and that's the answer. That's the answer. So limit with absolute value. You can do derivatives too, and you can do integrals, which we'll see what those are later. Those are also pretty tough. In general, anything with an absolute value is considered hard. Most people don't know how to do it. It's kind of like, they're in the book, but there's only a few, you know, it's the harder stuff. Maybe we should do another one. Do you all want to try one of these? Yeah, you do? Okay, so try this one. Limit x approaches, let's approach, oh, I guess I should make it harder, right? It's college. Let's approach -3 from the right. No, from the left. And we have x plus 3 over the absolute value of x plus 3. Take your time, see if you can do it. Really? All right, let's do it. Let's do it. I'm surprised that people are getting this. This is really hard. This is like tough. Okay. Solution. Draw a picture. So here's -3. We're approaching from the left, right? So that's over here. So we're going this way. So x is less than -3. So then you add 3 to both sides, right? So x plus 3 is less than 0. But yeah. So now that means that we replace the x plus 3 with a negative, right? So this will be this. And then we have x plus 3 over, and then it'll be negative parentheses x plus 3. Who got this far? Just curious. Wow, that's it. That's it. I mean, that's good. You make it this far, it's like you mess up after this, it's like -1. Like, I mean, this is like the key. This is the key step, right? So as long as you show this step, you're pretty much going to get. I mean, you're not going to mess up after this. I hope. You probably won't. So then this will just be -1. So you just get -1 again. So I didn't want to do the plus because the plus one's easy. The plus one, you just don't put the minus, right? So you think you got it? That's good. Good. All right, let's do something else. How about something with trig? Oh, I probably should mention this. If you have two continuous functions and you add them, you get a continuous function. So like all the trig functions are continuous, right? The sine, cosine. If you multiply continuous functions, you get a continuous function. If you divide them, you get a continuous function, as long as you're not dividing by 0 and stuff like that. If you take the composition of continuous functions, it's also continuous. So addition, subtraction, multiplication, division, composition, all of the operations are continuous as long as everything, all of those operations produce continuous functions as long as nothing is undefined. So like, for example, number 10 in the homework, or this is where I got the idea from. Number 10 in the homework is, whoops, fail. Number 10 in the homework, 10. I already forgot what it was. Do you have number 10 there? Anyone?
X equals 2x minus cosine x.
Cosine x. And it wants to know where it's not continuous, right? So the answer is, there is none, right? It's continuous everywhere. So I guess you would enter D and E or something, I'll look. But this is continuous everywhere. There's no discontinuities. Right? There's no fractions, there's no square roots, there's no asymptotes. This is continuous, this is continuous. When you subtract them, you get a continuous function. So everything is good, right? Everything is good. So, so for that one, you would just put none in the homework, and then you would just put NA, no discontinuity for that one. All right. Let's keep going with this notion of continuity. Let's do something else. There's a problem. Let me see if I can find it in the homework. It's number, yeah. Let's do number 16 from the homework. This problem is really tough. 16. So 16, they give us a piecewise function. Okay, so it's f of x equals, and it's 3 pieces. Okay, not just 2, so it's 3. So I think this might be the hardest one. So we have 8 if x is less than or equal to -3. Then we have ax plus b. Yeah, this is a good day to be here. Like, this is pretty tough stuff. -3 less than x less than 3. And then it's 8, not 3, sorry, 5. And then it's 8, -8. Who said that? Who got? That's a point. That's, yeah. Logan? No, it's good. No, it's fine. It's fine. It doesn't affect my life. I don't know why it bothers me. It shouldn't. X greater than or equal to 5. Give me the wrong. I'm like, no, it's fine, it's good. I usually start losing points. Yeah. Okay. Oh, what is the question? Find A and B so that the function is continuous everywhere. So find AB so that f is continuous. I'm going to go really slow as we do this one. This is really tough. Again, I was going to say something earlier and I forgot to say it. In the videos, there's a ton of videos on all of these questions, like especially from this section, because I was going to make some yesterday, and I clicked on the homework. I'm like, oh, I already have videos for all the hard ones, so I didn't make any. Like this is all there if you click on the videos. Okay, because you'll probably get stuck. There's a bunch of these. So we have to make this continuous. This is a really weird problem because you have three functions, right? So 8 is a horizontal line. By itself, it's continuous. Ax plus b is a straight line. It's kind of like mx plus b. By itself, it's continuous. -8 is a horizontal line. By itself, it's continuous. So basically, the idea is that you have, I'm going to erase this, but I'll draw it. You have 8, -8, and then you have to find the line that connects them to make it continuous. That's the idea, right? Because this is 8, this is -8, and so ax plus b is somewhere here. So you have to find a and b so that ax plus b actually connects these lines. That's a really deep way of thinking about the problem. A simpler way is this is continuous, this is continuous, this is continuous. But taken together as a whole, the function is probably not continuous. The only possible place that we can have a problem is at the endpoints. So -3 and 5. So when you're doing these problems, just focus on the -3 and the 5. So you have to make sure that this is continuous at those numbers. So first, -3. So first, let's do -3. So just do one at a time. So if you make it continuous at the endpoints, basically you're connecting it, right? Okay. So we had that definition of continuity. It had to be defined, the limit had to exist, and that third condition as well. So here's a really cheap trick. Whenever you have these problems and you have less thans and greater thans, use the second condition. So in other words, to make sure that this function is continuous at -3, well, it's defined obviously, because if you plug in -3, you get 8. The second condition is that the limit has to exist. For a limit to exist, it has to exist from the left and from the right. So because we have less thans and greater thans, this problem allows us to work that way. So take the limit from the left. So if you want to think of it in terms of steps, it's fine. Whenever you're doing these problems and you have less thans and greater thans, just do one at a time, and then just take one-sided limits. So the limit from the left, so we have to figure out what goes here. So if we're approaching from the left, which piece do you think we use?
The bottom, -8?
Oh, no, almost. Good try. 8. Yeah, why? Why the top piece? Why?
Because it's from x is less than -3.
Very good. This tells us x is less than -3, right? So we're approaching from the left, so you want to use the top piece. So you put an 8 here. Everyone see that? So because we're approaching from the left, we use the top piece. So you have to think, like, it's a beautiful question. Again, this is considered hard. There's a bunch of easy homework, but we'll do that later. This is good stuff. Easy limit, right? This is just 8. So now you drop the limit sign. Good stuff. So now we have to do it again to take the limit from the right. So I'm going to draw a little line here. So limit as x approaches -3 from the right. Which piece do you think we're going to use? First, second, or third? Second. Very good. Some people might say, oh, but 5, that's bigger than -3. You want to be really close to -3, but bigger. Wait, read it backwards. X bigger than -3. So the second piece. So here we're going to put ax plus b. Trying to go really slow because I know this is hard. It's pretty tough. So again, x is bigger than -3, right? So we're coming from that. Okay, so now we can actually plug in the -3 for the x. So we get -3a plus b. Good stuff. All right, so the limit from the left is 8. The limit from the right is this. We want the limit to exist, so they must be what? Equal. Oh my God, yes, 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 good. So you set them equal. Yes, very good. You set them equal to each other. Right? Because you want the limit to exist. That's the idea, right? That's the concept. This is a really deep conceptual question, right? That's why it's considered difficult, right? I just got goosebumps. So that's the first piece. So now we're going to go to the second piece. So now we have to do 5. So now let's do 5. So now 5. Yeah, this could be like if we had never done this in class and this was on a test. Can you imagine? Like, oh, that'd be like really tough. Yeah. Okay. So let's take the limit from the left. Limit from the left as x approaches 5. So which piece should we use when we're approaching 5 from the left?
Third.
Nope. Second. Yeah, because x is less than 5. Everyone see it? Good, good, good. So ax plus b. Ax plus b. Ax plus b. Good stuff. And so now we replace the x with 5 and we drop the limit sign, right? So it'll be 5a plus b. 5a plus b. 5a plus b. There's one on the worksheet like this, I think, too. All right, now we just got to do the limit from the right. So limit as x approaches 5 from the right. What is it, Logan? -8. Yeah, -8. Good. -8. So now you just plug it in and you just get -8. Let's see, -8. What do we do next with these? What do we do? Set them equal. Oh, so good. Wish I could just give you a name, but I can't do that. No, it's like, oh, eat the nose, like that's it, you know. But no, can't. Yeah. I wish it was that way. Like there was no test. Like you would just you got it in class. So like someday. So we have 2 equations. Ugh. We have to find a and b. So I guess we can solve them, right? Let's use Kramer's rule. No, I'm kidding. No. Do you remember Kramer's rule? 3 calc. Yeah, no, let's just solve it like a normal way, like how humans put it in a matrix. No, it's I'm just gonna write them above each other. So if 5a plus b equals -8, -3a plus b equals 8. Equals 8. To solve the system of equations, we could use substitution, I guess. It might be easier to just maybe multiply 1 by -1. I'm going to multiply the first one by -1. So multiplying the first one by -1, we'll get -5a minus b equals 8. Do that right? 8? Yeah, multiplying the first one by -1, -5a, -b, +8, +8. And then we can just add them, right? We can add now. So we get -8a. Adding the b's, we get 0 equals 16. Oh, this feels really good because now we get a really pretty answer, right? We get a equals -2. Yeah, really nice, right? Makes you feel like you're doing it right. Like, you get -2 on a test. You're like, yeah, you know you got it right. Maybe. I mean, I don't know. I think there's one on a worksheet where it's a fraction. It's like 4/3. It's like, what? But it actually is 4/3. Any questions so far on anything we've done? Any questions? Now we just got to find b, right? And we got this. So to find b, I'll write a little bit bigger because I'm getting farther away. So let's see. We can take the a and plug it in here, right? So we get 5 times -2, right? Plus b, plus little b, equals -8. Now it's harder. The camera has a harder time over here. Over here, the camera has an even harder time. It doesn't even, like, you can't even see anything. I learned that last semester the hard way. I started teaching over there. I was like, don't see anything. Like, whew, math. -10, right? 5 times -2 is -10. This is -10 plus little b is equal to -8. Add 10, right? It'd be really bad, like you mess up here, right? Like b equals 0. No. So b equals 2. That's it. Those are the answers. A is -2 and b is 2. So I would do another one. We probably should move on to another topic. So, but those are the steps. Let me just go through it one more time because this is a really tough problem. Is it going to be on the test? Maybe. I don't know. Like sometimes it is. It's considered hard. So whenever something like this does show up, like, you know, you got to be careful. So you have to find a and b so that the function is continuous everywhere. So this is, by themselves, these are all continuous functions. The only issue is possibly at the endpoints. So first you do -3. And so all you do, because you have less thans and greater thans, just take one-sided limits and make sure they're equal. So like approaching -3 from the left, x is less than -3, so we used 8. Approaching -3 from the right, x is bigger than -3, so we used ax plus b. Set them equal and you're here. Approaching 5 from the left, x is smaller than 5, so we're here, x less than 5, so ax plus b, so we're here. And then you plug in the 5 and you get here. Approaching 5 from the right, x is bigger than 5, so we use -8. And then you set them equal to each other. You solve the system, and then you get the answers. Any questions? Any questions on this one? So, anyone like this problem? Most people don't. Really? Okay. Wow. Good. Okay. Yeah, it's long. It's a longer problem. All right. Let's talk about something else. Let's talk about something called the intermediate value theorem. The intermediate value theorem. There's some in the homework with this. I was trying to like touch on all the topics, and then at some point again we'll go through. We'll knock out a bunch of homework. This is one of the big theorems in calculus. So intermediate. It's actually really easy, by the way. Intermediate value. It's just more to know though. So that's the thing, right? Intermediate value theorem. I think we talked about this before. In mathematics, a theorem is something that's been proven and is really, really important. So this is one of the big theorems in calculus. It's like one of the big theorems. You can abbreviate this with 3 letters, right? What letters can we use to abbreviate this? What do you think? IVT! Sounds like a drug. Yeah, IVT! Doesn't it? It's like, so IVT, bro! Yeah, no, IVT! Sounds like something dangerous. IVT. Oh, because IV, right, is that thing that, right, goes in your arm, right? What does it mean? Do you all know? Intravenous? Oh, that sounds, oh, okay. Yeah, I'll stick to it. Sounds gross. So suppose, by the way, if when you're doing the worksheet, if it says to verify the conditions, don't worry about it, right? Ignore that. So just, all you're going to have to do is find C. So suppose that, so these are the conditions. You're not going to have to verify these, not these. 1. So f is continuous. So it's continuous on the interval. So f is continuous. Continuous. There's that word again, right? UOU. Continuous on AB. So on AB. 2. The endpoints are not the same. All right. Then, I'm going to derail from my notes. I don't like what it says in my notes. It's from the book, but I'm going to change it to make it better, in my opinion. So f is continuous, and these are not the same. Then, for every number, so basically for every number, for every y value, so you have a continuous function here and here. And so I want to say that for every y value here, you're going to have an x value here. That's all it's saying. So if this is f of a, and this is f of b, for any y value, if I pick a y value, I get an x value. If I pick a y value, I get an x value. If I pick a y value, I get an x value. If I pick a y value, I get a... So f takes on every intermediate value. So given any y value, you have an x value. That's why it's called the intermediate value theorem. I'll explain it again in a minute. But for every k between f of a and f of b, f of a and f of b, erasers. For every k between f of a and f of b, there is a c. There exists. There could be more than one, right? So there exists a number c in AB. You know what that means? such that f of c is equal to k. So f takes on every intermediate value. I'll explain it again, then we'll do some homework problems. The homework actually has pretty good problems on this. It's got some really good ones. They're pretty good. So here's the idea behind this. I'll draw the picture I drew, but I'll draw it bigger. So if you understand the concept, that's awesome. Like when I took this class, I didn't understand the concepts. So I just memorized stuff and got an A. But that's fine too, but it's better to know. Like better to learn. So this is A, and this is B, and this is f of A. I was always really bad with concepts. Some people are really good with concepts. I was better at like showing work. So, yeah. So, and that was enough to get an A. So, so it's continuous. So if I draw the graph, I can't pick up my marker, right? So it has to look like this. And so basically, it's just saying that the function takes on every intermediate value between f of a and f of b, hence the name intermediate value theorem, right? So it takes on all values here. So if I pick a k here, right, then, yep, look, there's a c, such that f of c is equal to k. That's all it's saying. It's saying that for every y value, there's an x value. In other words, there's no holes or breaks. In other words, it's continuous. So it's intermediate value theorem. Intermediate value theorem. Yeah. Okay. So let's do some from the homework. Maybe we should start off. Let's do a couple of these. We got time. Let's do something easy. It's time for something easy. Like I feel like we've been doing hard stuff all day. How about number 18? 18 is a good, easy problem from the homework. 18. So 18, they give us a function. It says verify that it applies. Don't worry about verifying. So f of x equals x squared plus 9x plus 2. So plus 9x plus 2. And they give us the interval. The interval is 0, 7. Thank you. Great test question. This is always on the test, no matter what, right? And they tell us that f of c is equal to 38?
Yeah.
How do you know? Oh, how'd you know? How'd you know? Oh, I was like, where's your computer? I was like, whoa. I was like, you did it. You're like, oh. Yeah, all right. I was just like, no idea. It's good. Good stuff. Right, okay, so what's the question? Find C, find C. I zoned out, find C. See, you can zone out. I can't zone out, but you can, right? I was thinking about something completely, I was thinking like years ago, like in 2010 when I started teaching, no one had laptops. Like, it was very few people. Like, now like more people have laptops. I didn't even have a laptop. Okay. No, I didn't. So find C. So basically, they give us the function. This is the a and the b, and they give us this. This is the k, and we have to find C. So all you have to do in this problem is just write this down. And then just go from there. So step one, just write this down. I had a student once, and he got this wrong on the test. I remember. This is the only question he missed in the whole test. And I asked him why. He said, I just forgot how to do it. That's what he said. That's a story. He's a really smart guy. But he did everything except this one, and I couldn't believe it. So all you do is write this down. And then just plug in C for x, right? So c squared plus 9c plus 2. And what's that equal to? 38. Yep, it's all you got to do. It's really easy, right? So it's just a lot to know, right? Because we've done a lot today. We've done removable, non-removable. We did the thing with the absolute value. We did that thing with the a and the b. We're doing this. I mean, there's more. Like it's just a lot of information, which makes it hard. So all you do is you write this down, and then you have to solve for C. So maybe we can subtract the 38 from both sides. I haven't done this in like a long time, so I'm still coming back from my zone out. So this is going to be erasers. C squared plus 9c minus 30. Oh, this is actually a pretty good problem, I think. I think there's something tricky that's going to happen. I picked it because I thought it was easy, but no. It's easy, but it's tricky. This should factor. If it doesn't factor, at least in this section, that means you did it wrong. Later on, there's some that won't factor. We'll have to use the quadratic formula. But this type of problem should factor. However, there is one in the homework where you do have to use the quadratic formula. So, two numbers that multiply to negative 36 and add to 9. 12 and negative 3, yeah. 12 and negative 3, very good. 12 and negative 3, very good. What's your name, by the way? Thomas. Thomas. So you have a product equal to 0, so you said each piece equal to 0. I'm going to show this extra step because I did it in my differential equations class. And this guy's like, I've never seen that step. I'm like, oh. There's actually an or here. Yeah, you're supposed to put that there. You don't have to, though. This is called the zero product principle. When you have a product equal to 0, you set each factor equal to 0. You may say, why is there an or? Because this means that this is true or this is true. Or means one or the other or both. That means that these are both answers or one of them is an answer, right? They don't have to both be answers. At least one of them is an answer. Or in mathematics is not like or in English, right? Or in English is one or the other, right? It's like if you go to Burger King and you say, do you want cheese on your Whopper? You say yes or you say no. In mathematics, it's yes, no, and then yes, no is an option too. You can say both, right? That's a thing. That's a thing. Or in English is Zor in math. Anyways, we have two answers. Which one do you think we have to throw away? Negative 12. Why? It's not in the interval, right? So that was the tricky part, right? I didn't expect that when I picked this one. I just like, oh, it looked easy. I'm like, oh, it's easy. Oh, you know, I can do it in 30 seconds. But be careful. Nice test question. So we should do another one of these, I think. I feel like we should. Yeah, 19. Any questions on this one? All right, let's do 19. Let's do it. 19. Also a really great test question. So f of x equals x squared plus x over x minus 1. X squared plus x over x minus 1. And then we have our interval is 5 halves 4. Wow. So 5 halves, it's fraction, right? Like game over. And then f of c is equal to 6. It is. I believe you. I couldn't see it. Yeah, it's 6. Yeah. Oh, and everyone has the same numbers, which is really good. So that's really helpful. Do you all want to try it first? You want to try it? Yeah. Try it. Take your time. Try to do. Okay. First thing. I'll email the person in charge and I'll ask her if it's okay if you all participate. And then if she says yes, then maybe I'll even have her come in and talk to the class. So, good. All right, good stuff. Okay. So, hey, you were already here. So, you replace all the x's with c's. You can walk. Okay. No, it's okay. I'll go ahead. So basically, we have f of c equals 6. F of c equals 6. So replace all the x's with c's. So this is c squared plus c over c minus 1. Right? And then that whole thing equals c. I'm still thinking about the poster thing. I'll ask it. Yeah. I have samples and stuff. And yeah, it's good. All right. So what do we do next? This is where some people got stuck, I think. What do you do? Multiply. Yeah, by c minus 1 on both sides, right? Very good. C minus 1. C minus 1. So we get c squared plus c equals 6c minus 6. So 6c minus 6. 6c minus 6. All right, good stuff. This is a quadratic equation. Generally, when you're solving these, you want to set them equal to 0, right? So subtract 6c and add 6. Yeah. Would that be c squared minus 5c? Plus 6. And this should factor, right? This should factor nicely. This is c. We need two numbers that multiply to 6. Negative 3 and negative 2. So we get 3 and 2. Which one do we throw away? 2. Yeah, because 2 is smaller than 2.5, right? 2 is smaller than 2.5. So that would be the answer. Good. Yeah. I'll definitely find out about that project thing since you all, I'll do it. I'll do it. So it's more work for me because I have to look at your projects and make sure they're correct. Yeah. Any questions? Any questions on this one? On this one. All right. Do you all mind if we keep going for just like 20 more minutes before we break? You're okay? Like, can we keep going for like 20 more minutes? Is that okay? Okay. Let's keep going then. I want to talk about another topic now. So I'm going to write something on the board that is extremely useful. It's not even in the book, but it will help you a lot. I learned this in another class, like way beyond this, and yeah. So useful. And we're also going to use this next time in 1.5, so it works out perfectly. So sine x equals 0. Okay, so this is the same as saying, okay, I just have it memorized. X equals k pi, where k is an integer. Okay, where k is an integer. So by an integer we mean like 1, 2, 3, 4, 5, 0, and all the negatives as well, like -3, -4, -7. So whenever sine is equal to 0, x is equal to k pi. So like pi, 2 pi, 3 pi, negative pi, 4 pi, 20 pi, all of those. So there's infinitely many solutions to this equation, and they all have this form. You could probably figure it out, like just for fun. If you drew the unit circle, on the unit circle, sine is the y coordinate, right? So it's the y coordinate. So this is 0, this is pi. So sine is 0 here, it's 0 here, it's 0 at 2 pi, it's 0 at negative pi, it's 0 at 4 pi, it's 0 at 3 pi, etc. Anything times pi, sine is going to be 0, okay? So it's worth memorizing if you're going into any type of math or engineering, stuff like that. You will see this again. The second one, but again, it's not in the book, it's weird. Cosine x is equal to 0, and this is equivalent to x equals pi over 2 plus k pi, where k is an integer, where k is an integer. A lot of information today, like tons, it's so much information, but it's good for you. Make your brain grow, right? Like, I mean, it's a lot, it's crazy. So you can also reason it this way here, like, so on the unit circle, cosine is the x coordinate, right? So it's cosine of pi over 2 is 0. So if you're at pi over 2, you can add pi or 2 pi or subtract 2 pi, or subtract any number of pi's, and you're going to get 0 because you'll be here or here no matter what. So this is extremely useful to know it's just from math. I guess you're supposed to learn it in Trig, but I know when I teach Trig, I don't. Oh, that's not true, I do it. But I don't do much with it, right? Because there's no homework problems that require it in Trig. So have you all seen this before? Anyone? Kind of, maybe? No? Yeah. So what is this for? Well, when we're given a trig function and we have to find the discontinuities, we're going to use this, right? In the next section, it's the same, except we're going to find the vertical asymptotes. So let's do a couple. Actually, let me just make one up. Because I think the homework ones might be a little bit easier. So let's find the discontinuities. And we'll also talk about whether or not they're removable or non-removable. You'll see. So here we go. Let's do a couple of these. Let's do like more than one example. F of x equals, okay, how about this one? Tangent, let's keep it, this is college. 3 pi x over 2. I'll put a 4 here too, game over. Make it hard. Hardest possible problem. Okay. So you're trying to find out where this is not continuous. So, I mean, I guess you could have the tangent graph memorized, but that's more work. Tangent is what over what? What's on the bottom? Sine over cosine. So a good first step is to maybe like rewrite it that way. So like this, 3 pi x over 2. And then here we have cosine 3 pi x over 2. So now you're thinking, okay, this function, where is it not continuous? Well, it's going to be discontinuous whenever the bottom is 0. right? Because you can't divide by 0. So what you do is you set the bottom equal to 0 to find out where it's messed up. Where is it not continuous? So you set cosine of 3 pi x over 2 equal to 0. Let me pause here. I'll let you catch up. Let me go slow. Set the bottom equal to 0. So again, you're looking for where it's not continuous. It's going to be not continuous whenever the bottom is 0. So whenever you're doing these and you see whenever you see a trig function here, if it's not sine or cosine, think about what's on the bottom. Okay, cosine's on the bottom, so you set this equal to 0. Okay, you can skip steps here too. You don't have to show this work. So when is cosine equal to 0? Well, the cosine of blah is equal to 0 when blah equals that, right? Just think of x as like something, right? So this is your x. So this is your x. So you just take this and you set it equal to pi over 2 plus k pi. Okay, so now we have 3 pi x over 2 equals pi over 2 plus k pi. Okay. When you're studying for the test, it's really useful to go over your notes as well, right? Some of the homework is easier, right? So again, so you can go from here to here. How? Oh, it's tangent. Cosine's in the bottom. Oh, cosine will be 0 at pi over 2 plus k pi. So you just take this, set it equal to pi over 2 plus k pi. Just think about what's on the bottom, and then so like if it was cotangent, you would just set this equal to k pi, because sine's in the bottom. So just think about what's on the bottom. Or, I say bottom, what's the bottom actually called? The what? Yeah, I know, I just hate saying it because it's denominator. It's like denominator. It's 5 syllables, or bottom. It's much easier on the tongue to say bottom than denominator. Any questions? Any questions up to here on this one? All right, we have to solve for x. So to get rid of the 3 pi over 2, we can multiply by what is that called? That thing we flip it. What is that called when you flip it? What is it? Reciprocal. The reciprocal. You know, I didn't know what that was for years. Yeah, it's called the reciprocal. So I'm going to show every step. I'm going to put a 2 over 3 pi here. And I'm going to put one here. I'm going to show, you can skip steps. I'm just going to show every step. I'm not going to skip any of them. This is equal to, and again, you can skip steps. I won't do it, but you can. Pi over 2 times, just distribute this to each piece, times 2, starting to fade, 2 over 3 pi. That's right. All right, so far so good. Plus, pi is falling out apart, k pi times 2 over 3 pi. Yeah, I used to always skip steps here, and then one semester there was this girl, and she turned in her test, and she was showing all the work. I'm like, oh, she's doomed. She got 100. And she showed all the steps here. So ever since then, I show the steps. People always mess up here. So now I always show all the steps. So this times this, plus this times this. The pi's cancel, the 2's cancel, right? So you get x equals 1/3 plus the pi's cancel. So you get 2k over 3. Very good, 2k over 3. And we forgot to say something. We still have to say this, right? This k is an integer. So it's important to say that. It's not true for all k, just when k is an integer. So where k is an integer. I like how full this class is. This is this is the fullest Calculus 1 class I've had in like 3 or 4 years. Because I always do the honors, and honors only has like 15 people, 20 people. And I haven't had 30 in like. It's good. It's good. Yeah. More brain power. Yeah. Think about it. If we could take everyone's brain power and combine it into one, right? Can you imagine? We rule the world, right? Take all the intelligence in this room and put it into like one brain. So think about what's on the bottom. Set it equal to 0, and then just take whatever is here and set it equal to pi over 2 plus k pi. Solve for x, and then there you are. These are vertical asymptotes. Are they removable or non-removable? Non-removable. Yeah, these are non-removable. So I'm going to write that because I think the homework wants that. Non-removable. non-removable. In the next section, we're going to do this again. So we're doing this again next time, except in the next section, it'll say find the vertical asymptotes. On your test, it'll probably say find the vertical asymptotes. So we should do maybe, let's do one more of these. I'll write one on the board. I'm going to erase this. You have it memorized, right? So yeah. Yeah, Ethan?
So you don't do anything of the form or the sign?
No. I know, yeah, because you only care about what's going on the bottom, right? Or the denominator. So you rewrite it. You say, when is this undefined? Whenever the bottom is 0. So you just set the bottom equal to 0. Good. Any other questions on this one? Anyone have questions?
You don't even know what K is? So K is just anything?
K could be any number, any integer. Any other questions? All right. How about this one? Try this one. B. A little bit easier. B. Let's call it little g. Little g of x equals, let's do an evil function. Cosecant of 2x. Try this one, see if you can do this one. Solution. So first thing you do is rewrite it. So cosecant is 1 over which function? Sine. So step 1, you do this, right? Rewrite it like this. That's the first step. Then you have to think about when this is undefined. That's going to happen when the denominator is equal to 0. So that means that sine 2x equals 0, right? Because you're trying to find out when this is undefined. So you always just take this and set it equal to 0. Okay, ignore everything else. Now you have to use the formula. Remember the formula was sine x equals 0 is the same as x equals k pi, where k is an integer. So in this case, it's not x, it's 2x. So you take 2x, and you set it equal to k pi. Okay, and then to finish, you just divide by 2. So divide by 2, divide by 2. So we get x equals k pi over 2. Now I had mentioned that you're supposed to say where k is an integer. I'll show you a shortcut. Why not? You're supposed to learn stuff. It's college. So you can do the following. You can say, put a comma and then just say k. And then you do this symbol here like this. It means is an element of or belongs to. And then you draw this fancy z like that. So that's an acceptable answer. That's a comma. So what does this mean? So this means is in, belongs to is a member of, and this set is this. It's equal to the set, and it's dot, 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 -2, -1, 0, 1, 2, dot, dot, dot. This is the set of integers. Set of integers. This is not in the book. Set of integers. The reason that we use the word z, the letter z, it comes from German. I don't speak German, but according to Wikipedia, anyone know what the German word for numbers is? Zahlen. That's how you say it. It sounds scary. So Zahlen. Yeah. So that's the German word for numbers, or is Zahlen. The German word for numbers is Zahlen, and so historically they use z because the Germans created a lot of mathematics, right? So a lot of the math symbols come from those places, right? There's the mathematical languages are French, German, and Russian. Those are the math languages. So like if you get a PhD at a good school, you have to learn one of those languages. Weird, right? Some schools accept Chinese, but it's pretty rare. So usually it's French, German, or Russian because a lot of the old math is published in those languages. Anyways, so you could do that. You could do that. Another way to do it. Yeah.
What did you learn?
Oh, I don't know. I didn't get a PhD, so no, yeah.
They don't make you do for a master's. It's only just for.
I never took the test. Yeah, I think I had like 3 years to do it, and I just didn't do it. Yeah. Yeah, no, didn't do it. Yep. Any questions? Some schools don't require it. Like UCF doesn't require it. You don't have to. But like other schools, like Princeton, Notre Dame gives you a year. That's it. Right. Yeah, after 2 semesters, you have to pass the test or you're done. Like, do you have to leave?
Yeah, after the war.
Oh, okay. Bye.
Which one would you have done?
French.
Yeah.
Yeah, because it's closer to Spanish, and I speak Spanish, so it's a little bit easier, right? Right. I probably would. I mean, it's a very pretty language. Yeah. Totally would have done French. Yeah. What's the recording? No, I'm kidding. I was born there, yeah. I speak Spanish. It's my first language. Okay, any questions on this one? Any questions on this one? Make it weird? Delete this part of the video. Delete, 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 delete. I don't watch these because they take, I don't watch, so hopefully I don't leave it in. Apparently I was eating in one of the videos. Someone posted a comment like, you were eating? I'm like, what's going on? Oh, we have to do this one. We have to do this problem. We have to do it before I forget. Number 17, let's do it. This problem is deceptively easy/tricky. So if I don't do it, it's really hard to explain. So let's do it. F of x equals, hey, all right. Oh, it's g of x. G of x. Are you sure? That's not a mistake? Is that a spelling error?
No, that's a spelling error.
Spelling? Okay. All right. I'll take it. I'll take it. Thanks, Logan. It'd be really bad or great, depending on how you think of it, if like whenever you answered a question wrong, you lost a point. Can you imagine? Like, oh, no, I'm not going to do that. That's just wrong. Like, oh, I already lost 15 points. There's no way I can get an A. Like, it's bad. It's bad. All right. What is the question? Find A so that the function is continuous, right? So find A so that f is continuous. So find A so that the function is continuous. This problem is really tricky. I remember the first time I taught this class, I'm like, I was looking at the homework and I'm like, I know how to get the answer, but why? And it took me some time to like think about the reason why my work was correct. It's really sneaky. So let's do it. Solution. So we did one like this before and we had to find A and B. That was harder, right? So here's just A. The difference was, though, on the one where we had to find A and B, we had less thans and greater thans. Remember that? And so we approached from the left and from the right. Because when you have a less than, you know, like, oh, it's like, so if it says less than 3, you know if you approach from the left, you're going to use this piece. If it says greater than 3, you know if you approach from the right, you're going to use this piece because it's bigger. But here, there's no less thans or greater thans. So we can't do that, right? So what do? Well, what we have to do is use the third condition of continuity. The third condition of continuity was that condition 3, I'll write it here, was limit as x approaches A, right? That's what we care about here, A, of g of x equals g of A. That was condition 3. I just replaced g with f and c with A. I think I said that right. Yes?
So wait, you said find at?
Find A so that f is continuous.
Wait, is it f supposed to be?
That's supposed to be G.
Okay.
Okay, I should just give you all the points. Okay, Logan and what's your name? John? John. Good. No, it's good. It's good. Yeah, it's all right. Doesn't affect my life, right? No one sees your grades. Doesn't matter. Okay, so condition 3 was that has no effect on my life. Doesn't matter. In 20 years it won't matter. Okay, so we have to do this. So that's condition 3. So let's go ahead and work out this piece first, G of A. So G of A is equal to, what would G of A be in this case? 2. Very good, Logan. Everyone see why it's 2? Because when x is A, you get 2, right? When x is A, you get 2. So G of A is 2, right? G of A is 2. Bless you. I saw it coming. I saw you like start to sneeze. I'm like, oh, she's going to sneeze. This is G. Sorry. So G of A is equal to 2. G of A is equal to 2. All right. So now we have to use this condition here. So I'm going to go ahead and write this down. Limit. This is where I was like, what's going on? Like, so I think I said this the first day of class, but I never wrote it down. So when you're taking a limit, you only care about what's happening when x is close to A, right? You don't care about what's happening when x is equal to A. So in fact, during this entire process in your mind, x is not equal to A. So because you only care about what's happening when you're close to A, so x is not necessarily equal to A. So in this case, when x is not equal to A, we use the top piece. That's the trick. So the trick is to use the top piece because when you're taking limits, x is not equal to what it's approaching. I just remembered something that I have to show you. So I'm like, I can't forget. Something really cool, like really cool. It'll only take 2 minutes too, but it's really important. Okay, so now, oh, what can we do here to make it easier to do this? What should we do with the top? Factor, yeah, factor. We could factor this, right? X approaches a, so we have x minus a, x plus a, over x minus a, right? Right. So I think we've done more calculus today than any day so far this semester. Like this is like really hard problems. Boom! Right. This is limit x approaches a, x plus a. Right. So these cancel. So we're left with this. I'll pause and let you catch up, so you can catch up. Falling, trying to get out of the camera. So now, what do we do next? Plug in, yeah, plug in. Do we write the limit sign? No. A plus a, which is 2a. So the limit is equal to 2a. But we want it to be equal to g of a. So we set 2a equal to 2. Good, Elizabeth. No. Really? I just guessed. Okay. So then you divide. Good, Elizabeth. Then divide by 2, so you get a equals 1. That's it. Let me go over it one more time. This is pretty tough. So this is the only one like this in the homework, too. So it's like, where do you get more practice? You don't, right? Like this is, just make sure you can do this one. You see the problem? You have to find a so that g is continuous. Normally, you would take limits from the left and the right. But it's a not equal to sign, so you can't do that. So you should probably resort to this condition here. So g of a is equal to 2, because when x is a, g of a is 2. Take the limit. When you're approaching a, it doesn't matter what happens at a, just when you're close to a. So x is not equal to a, so you use this piece. Factor, plug it in, you get 2a. You want this to be true, so this is 2a, this is 2. This is 2a, this is 2. So you set them equal to each other, and then you just solve for a, and you get 1. I want to show you one more thing, and then we can do some homework. Any questions on this? Okay, this is really important. So I don't know if you remember the very first day of class, I told you that whenever you're taking limits, the first thing you should do is just plug the number in, right? And you can do that. But I never told you why, right? And then here, I was just saying that, oh, you know, whenever you're taking the limit, x is not equal to that. In other words, I was just saying you're not supposed to plug it in. So why are we plugging it in? Right? You're not supposed to do it, right? X is, when you're doing this, x is, you could put this here, it would still be correct. X is not equal to a throughout this entire process. Even here, x is not equal to a, right? But then we're plugging it in. How? Here's why. This is why. So this is why we plug numbers in, right? No one ever talks about this. Check this out. So aside. Say we have, let's go really easy. Limit x approaches 2 of x squared plus 1. Okay, so let's just take this limit. So in this case, we can plug the number in, right? So it's super easy. So we just get 2 squared plus 1, right? So we get 4 plus 1. So we get 5. Right, yeah, 5. Okay. Okay. So why? Check this out. Think of this as f of x. So if you take the limit as x approaches 2 of f of x. F of x, x squared plus 1, that's continuous, right? It's a parabola, right? That has no holes or breaks, right? So according to the definition of continuity, this is equal to f of 2, right? Remember, x approaches c of f of x equals f of c. That's the definition of continuity, right? So because this is a continuous function, this is true. But wait a minute, what is this? This is the limit as x approaches 2. F of x is what we have on the board, x squared plus 1. F of 2, we just did it up here, right? F of 2 is 5. So every time we plug in a number and we get the answer, we're using continuity. Every single time. So when you're taking limits and the homework and you plug in a number like this, you're using the power of continuity without even knowing it. It's kind of weird, right? It's kind of weird. Deep, right? So again, we plug in the number, we get 5. Think of the definition of continuity, right? This is what it means for a function to be continuous at 2. That, right? Because this is the regular definition, right? X approaches C. This is the definition of continuity at C, right? So this is continuous at 2. Well, this is continuous everywhere, right? It looks like this. So it's continuous everywhere. In particular, it's continuous at 2. So you can just plug the 2 in. So every time you plug a number in, you're using continuity. Every single time. It's kind of weird. People don't really think about that when they're taking limits. I'm like, oh, just plug it in, you get the answer, it's good. But you're using the power of continuity. Weird, right? Really weird type stuff. Maybe we should do some homework, do some easy problems, and then take a break. So I'm going to stop this because it's not going to like record